Hi. So we talked about conductors and how they allow the electron flow through the conductors. Now we're going to talk about something called resistance and resistivity. Okay, resistance and resistivity. So we know that every conductor conducts electric charge to a greater or lesser extent. And some of the great conductors out there were we've had gold, silver, copper's a good one. Our resistivity and resistance, okay, of a particular length of wire can be measured to pretty good accuracy using the formula R. Okay. Now let's look at this formula. This is a constant. Okay, this is measured. This is a rho. This is the length of the wire. This is a cross-sectional area of the wire. Okay, this is measured in ohms. Okay, length, the L, is measured in meters. So we'll say the resistance is measured in ohms, the length is measured in meters, and resistivity, or rho, is measured in ohm meter. Okay, so we're going to take a peek at several different wires with different materials, and this resistivity can be easily found in a chart. So if we want to find the resistivity, okay, rho, okay, I'm going to try to draw it like that, is equal to the resistance times the cross-sectional area over the length. So this can be found with different lengths of wire and cross-sectional areas of wire. So look how this plays out. The resistivity, how resistant the wire is to electron flow, depends on the resistance of the material, okay, which doesn't change, the cross-sectional area of the material. So let's say we've got a wire here. Okay, we're talking about this area, shaded area right here. And then the length. So notice, as the length goes up, the resistivity goes down. As the area goes up, the resistivity goes up. And then also the resistance of the particular material, the R of the material, as it goes up, this also goes up. Okay, it makes sense in terms, if you think of it as a hose again. If I have a tiny, tiny little hose here, okay, which represents a small cross-sectional area, okay, this is going to be pretty small here. Okay, and furthermore, if I've got a long wire that's very thin, okay, it's going to be pretty resistive. It's going to have a resistivity that's pretty high based on the fact that this length gets longer and longer. Now, when I'm working on a boat and I'm working with direct current, okay, I can only go so long with the wires before the voltage starts to drop. Okay, because we know from the past video that the voltage can drop if the resistance changes. So I can only go so long with my wires before I start having to increase the voltage to get a better possible flow. Okay, so a nice thick wire, okay, would be something like this. Okay, a nice thick wire would increase the cross-sectional area and thus, the resistivity of the wire. So nice thick wire, I can get pretty good voltage and current flow. Okay, so the current can flow through this pretty easily. The wire is really thin, then you're not going to get that good of a current flow. Now, if anybody's ever installed their own speakers in their car, they can attest that the speaker kits, usually that you get to install speakers and amplifiers, the wires are really thick. Okay, they have a big cross-sectional area because in speakers you want as much power to travel through that as you can get. So I'm going to direct you to the note. I'm also probably going to give you a printout, but different metals or materials have different resistivities. There's a chart that shows you what these numbers are, and you can use those to figure out what kind of current can flow through.